Just let me say good morning, dear friends of ISSI in Europe, good evening in Asia, and a very early good morning to anyone who may join us from more westerly parts of the world, if there is anybody amongst us. I'm Tilman Spohn. I'm the Executive Director of the International Space Science Institute here in Bern, in Switzerland. And I will be introducing the first 7 talks of our new online seminar series. And my colleague Suliba will moderate the meeting and take care of the questions and raise your hands and so forth. Well, ISSI, as you may know, is known for providing space scientists with a forum for meeting in person. And we will continue to do that, no question about that. But the COVID-19 pandemic is enforcing digitalization on everybody. And it motivated us to try a new online tool with our Game Changers seminar. So why Game Changers? I think it's fair to say that nothing changes our understanding of space more than missions. How often, at least I did we think we knew what to expect when we launched a mission, only to find that things were very different when we got there. So that was my experience in Rosetta or Mars missions and so forth. And some missions have started entirely new ball games. So we thought that it would be interesting to have experts and participants in missions review just how the games have changed, through their missions. So we will spend August and September with talks on solar system exploration missions, to be followed by solar and solar environment missions in October. November and December, we are planning for astronomy and astrophysics mission, including cosmology. Our choice of missions was difficult, and it's certainly biased, for which I apologize, but I think we have a broad setup. We will look at asteroids and comets. We will look at our neighboring planets Mars and Venus, at Titan, at Jupiter, and peek into the far reaches of our solar system with the New Horizons missions in 2 weeks' time. So not next week, but in 2 weeks' time on August 13th. But I'm glad we start this series off with a talk on the Hayabusa missions that are marveled by space experts and nerds alike for the ingenuity and as the first sample return mission from asteroids. And I'm very glad that we have our speaker today, Professor Seiji Sugita from the University of Tokyo, who in addition to being a pioneer researcher, is the science PI of the navigation camera on Hayabusa 2. Seiji, you have the floor, and I'm looking very much forward to your talk.
Thank you, Tilman, for the wonderful introduction. Today, I'd like to talk to you about 2 missions, Hayabusa and Hayabusa 2. And thank you for coming. I see 134 people in the audience. Because Hayabusa 2, Hayabusa's are 2 missions, I'll talk to you about Hayabusa mission first in the context of how the first mission prepared for our Hayabusa 2. What did we learn about the Itokawa, but what did we learn about the space mission to the asteroid in general? And then move on to the Hayabusa 2 mission. And from the beginning of the launch of Hayabusa, it's been 17 years. So understanding of an asteroid has changed greatly. And hopefully by the time we have a sample by the end of this year, we'll begin to see the major change in understanding of asteroid. And, that's the second part of my talk. Okay, here's some little summary of a timeline of a Hayabusa original mission. Here's a little YouTube movie of a launch. The sound isn't that great, but you can see. It's a very fast liftoff because it's a solid fuel rocket, M5. It's much smaller than the H-2A used for Hayabusa 2, but the mass of the spacecraft of Hayabusa wasn't that much smaller than Hayabusa 2. So that's a brother and sister. I don't know which is a brother and sister, but so very similar in structure. And after the launch in 2003, 2 years of a good cruising, Hayabusa spacecraft arrived at the first S-type nearest asteroid Itokawa in September of 2005. The shape and then the surface texture was very different from what we expected before. Well, except for the Thomas Mueller predicted correctly the roughness of a surface, but well, also the shape was somewhat oblong, but the very vivid image was very surprising. So far it was good, but by the time he made the first touchdown, there's the spacecraft began to have a little malfunction because that was the first mission, first ion engine, and then first mission to asteroid. It began to have some problem, but and then in particular they lost the control of most of the reaction wheels and also chemical propulsion system. So the returning trip was much more agonizing. But 4 years and a half of endurance, the engineering team and scientists made it to the Earth, 2010. And then here's, this is the last image of the Earth before its arrival. And then here's a movie clip captured by NASA Ames people, Peter Jenkins and his colleagues of US naval aircraft. You can see that big flash here is a ablation from the main spacecraft. And then this small dot here is a capsule that can withstand the atmospheric reentry. The initial speed is the same because it was coming from the same speed, but the main spacecraft quickly disintegrates because it was not designed to do this. The capsule withstood the aerodynamic heating. Then finally made it to the surface of Australia. So that was really a literally flashy moment after this huge troubled journey. And oh, I forgot to mention that the touchdown was conducted, but the firing of projectiles and other things were not really perfectly conducted. So people are very, very worried about outcome of the sample return. Hey, what kind of a sample did we have? But I'll show you not in this next picture, but as many of you may know, there are a lot of samples, but the mass was very small, more than 1,500 grains, but less than 1 millimeter of grains. But that was sufficient to let the scientists, mostly geochemists, conduct the major research. Okay, before I go to the sample analysis, I will quickly review what we learned out of remote sensing observation of Itokawa. The first knowledge we think we learned is the fact that such small asteroid, this has about 500 meters of a long axis, is a rubble pile. It's not a monolith as other larger asteroids visited by other spacecraft. That was a first clear rubble pile asteroid. Fujiwara concluded that because the measured porosity was very, well, estimated porosity was very high, shape was very odd, but it's consistent with the possible accumulated blobs of material colliding later in accumulation process, and also more importantly, the large number of large blocky boulders are everywhere, consistent with the reaccumulated fragments from catastrophic disruption as predicted by theoretical calculation and the laboratory experiments by Fujiwara himself. And then Another important finding was the presence of a space weathering. Space weathering on asteroid has been long suspected, but there's a lot of controversies because those small asteroids may not be able to retain dusty, small fine-grained dust, which would carry the space weathering. The impact on other radiation may create some space weathering in small fine-grained material, but those may not be able to stay in such a microgravity body. So there are a lot of different ways of looking at the different types of colors of small asteroid. But when we went there, the near-infrared spectra of asteroid Itokawa in two different locations, for example, exhibited very clear evidence for space weather. Well, I may not be able to say clear evidence, but the difference between, well, the observed spectra could be reproduced very well by adding LL chondrite spectra plus nanophase ion spectra. Nanophase ion are considered to be the source of a space weathered spectra. When you add those things together, the observed spectra was reproduced really well. And also the darker location, brighter location was consistent with the geopotential highs and lows. Geopotential low place should accumulate older, more space weathered material. And that's where those darker material was found. And then lighter, less space weathered material was found on geopotential high. And then, so that was a very strong support for the presence of space weathering. And furthermore, the mass evidence for mass motion and resurfacing on such a small asteroid was also found. A lot of people suspected it, but it wasn't really clear how such a mass motion and resurfacing happens on those microgravity. And then this is a sorry, just hitting the bottom. Miyamoto and colleagues found that many boulders tend to have alignment of a longer axis parallel to the, well, perpendicular to the geopotential slope. And then clear preference of alignment of those boulders as shown in this diagram. This is the lower axis is an angle and the y-axis is the population. It's a histogram. Similar thing also found another slope, but on this slope, the boulders are imbricated. Imbrication is the flat boulders are located in this kind of fashion. I don't know how to say in English very well, but it's not really flat on the surface, but it's in place in an angle in this motion. When those blocks are rolling down the slope, they tend to stop on an angle, and then it's kind of stacked together. And that's shown over here. It's not everywhere, but in many locations of Itokawa have those classic way of invocations and alignment of boulders. So those are one of the pieces of evidence to show there is a clear mass motion even in this microgravity environment. Then from those geomorphologic observation, we could figure out, and also from shape modeling, we can calculate how much of a geopotential does exist on the different parts of an asteroid. For example, the neck region the sort of more like the belly or back region of this asteroids got lower geopotential, which tend to accumulate older material and then more stably. So space weathering, well, material that experience a longer time of space weathering should accumulate over here, as opposed to the top of those um, head and tail of this asteroid. And then making the long story a little short, we conducted the principal component analysis of a multicolor band of Itokawa. We found that index for space weathering, consistent with this Hiroi finding, also the S-type asteroid in the main belt, geopotential low does have a higher space weather index compared to those geopotential high locations. And furthermore, the extent of a variation of those space weathering young and then more heavily space weathered spectra is almost as large, as great as the variation of the entire S complex in the main belt. By this I mean, this is the entire so-called S-type asteroid clusters in the main belt by the Tedesco et al. It's called a ECAS, 8-color asteroid survey dataset. They measured several hundreds of asteroid and then compiled into a data set. But when we conduct the principal component analysis decomposition, all these variants of S-type asteroids form like this kind of cluster. This one is a CX complex. Ryugu and Bennu belongs to this cluster, but the Ryugu and Itokawa and the other S-type anhydrous silicate asteroid existing here. This is the entire main belt S-types, but just small half a kilometer wide spectra, asteroid spectra. Itokawa has a spectral range almost as wide as the entire S-type complex. So this really is interesting. This entire S-type some of the variation among the clusters could be projected into this Itokawa itself. It's a very small asteroid, but its variation can be projected back to the S-type cluster. The similarly space weathered asteroid may be found in other parts of the main belt. By the way, the Itokawa is a near-Earth asteroid, but it was probably coming from the main belt by the gravity perturbation of Jupiter and Saturn in the relatively recent past. So it's a good analog of a main belt. And furthermore, this trend of elongation or spectral trend is consistent with the space weathering trend from an ordinary chondrite, starting from a fresh material with a small bit of irradiation. In this case, it's a laser and then also charged particle coming from the left-hand side to the right-hand side of this PC domain. Very consistent among the three experiments. Main belt observation, Itokawa disk resolved spectra, and then the laboratory space weathering experiments. All these things are consistent. It is really showing that the Itokawa is not just small one dot of a piece of rock, but it's got some geology and some evolution and the rejuvenation of the surface as possibly as uh, various as the entire S-type complex in the main belt. Okay, so so this is the what we think we learned. Well, just a small bit of what we learned in remote sensing. How do we compare with the samples? Here's one example of a Itokawa sample brought by the Hayabusa spacecraft. And this is another example. This is a optical microscope image. It's relatively large sample, as large as 100 micrometer. I have to say it's small, but we got luckily more than 1,500 particles. Geochemists had a hard time really analyzing everything in such a small space, but they did a wonderful job. I just showed only Japanese contribution here, but I know there are a lot of international contribution of this geochemical analysis. One example of the initial analysis of the Hayabusa 2 team is the mineralogy. They found lots of minerals expected to for the LL type ordinary chondrites, and then they found olivine, low calcium pyroxene, chromite, and then high calcium pyroxene was somewhere, but I don't really see here. But those mineralogies are consistent. And then from the measurement of calcium and other elements in low calcium pyroxene, high calcium pyroxene, they can measure the equilibrium temperature that these species must have experienced. And that those temperatures are, oh, I forgot the name. Yeah, here, it's 800 degrees. To reach that temperature, the parent body must be 20 kilometers or larger at the time of aluminum-26 heat source was still available. So those small pieces of particles could really give us evidence or the information about the temperature history, thermal history of a parent body of Itokawa. It's important to note that it's a parent body, not the Itokawa itself, because Itokawa was too small to reach this condition. And then another piece of evidence is again, the space weathering. Even though we think we saw the piece of evidence of space weathering at the time when the spacecraft was hovering around the Itokawa, the return sample really showed us the very clear evidence for the space weathering here. This Noguchi et al. Paper shows the presence of lots of Fe-rich nanophase in this amorphous layer on the surface of those small particles. The scale bar here is very small. It's only 20 nanometers across. This one is about not 1,000 times, or almost 1,000 times, 500 times greater here. It's a SEM, it's a TEM, transmission electron microscope. This property here he found on a real Itokawa particle is very similar to what Shosasaki created in the olivine powder in his lab with the laser irradiation. The exact shape is different, but the fact that there's a amorphous layer and an embedded very small nanophase ion is the same. So it's very, and also same thing is found in the lunar samples. So this discovery really shows that a very similar process must have been going on the surface of the Itokawa. So even though the space weathering is a very literally superficial phenomena, but it does change the color of material or the surface of Itokawa. It's very important to understand this process in order to connect the telescopic data of a main belt, lots of asteroid, to the sample we have on Earth, such as ordinary chondrites and other material. And then this one piece of thin section really connects those two things together. Okay, and then putting those pieces of evidence as well as other geochemical measurements together. This is a very good summary diagram of what we think we know about the parent body of Itokawa. The original parent body must have been a LL chondrite-like parent body. Its size must be larger than 20 kilometers in radius. And then the temperature range is about 600, 800 degrees. And then the age of a thermal metamorphism was also measured by the measurement of extinct isotope, such as 26 aluminum. And then a catastrophic impact must have happened. Many isotopic clock measurements was conducted. What I thought really promising is the argon-argon dating by Park et al. And then the uranium lead age measurement by Terada. And those two are pointing toward about the 1.4 giga billion years of disruption age. That is actually consistent with the Flora family. Well, I don't think it's a very firm evidence to say that, hey, Itokawa was from a Flora family, because there are a lot of similar spectral families and then asteroids in the inner belt of a main belt from which Itokawa is from. But Flora family does look like a very promising original family of Itokawa. And then the Flora mass is more than 20 kilometers in diameter. So all these stories seems to be consistent. And then after the catastrophic disruption, the rubble pile can be formed. Very detailed calculation has been done by Patrick Michel and then Derek Richardson, others. And then this story seems to be straightforward, although it's not that easy to figure out, but the lot of theoretical calculation supports that this scenario is very viable. And then later on, galactic cosmic ray exposure age, and then also solar wind exposure age has been measured. Galactic cosmic ray age was about 8 million years or less. And then solar wind exposure age was about 1,000 years. And this is very superficial process, and then the galactic cosmic ray can reach up to meter or 50 centimeters. So the convection, granular convection of the Ryugu surface is maybe some million years or a little longer, could be possibly, for meter scale of thickness. And then sub-millimeter or millimeter thickness of resurfacing could happen in a very short period of time. So very small scale to a large scale, very short time scale to a long time scale of evolution can be portrayed by these wonderful suite of geochemical measurement. So I felt that, hey, this is a really good reason why we have to go back to the asteroid and bring back the samples. Okay, so learning about the Itokawa was so good, but to me, the member of a Hayabusa 2 science team, this was a very good template for planning what kind of a measurement or analysis we have to do for the Hayabusa 2. And then that was really helpful for planning our observations, and then how to connect the nanometer scale geochemistry to AU scale main belt asteroid and telescope. And this is I think it's as important as engineering technology for asteroid sample return. Okay. I think I spent too much time in talking about the Itokawa, but I think I'm gonna keep going for the Hayabusa 2. All right, so now the Hayabusa 2 mission happened. Maybe too large, I don't know. So this is a H2A rocket. It's not that important, but I just want to show that it was launched. And then the rocket was much bigger, but the spacecraft itself is just slightly larger. And then M5 was not available at the time of 2014. And then liftoff was a little bit more gentle. And then 4 years later, we arrived at the asteroid Ryugu. And this is the first bunch of pictures taken at the home position from asteroid Ryugu. There's a lot of operations to be done, and then those are called the heritage operation, although it was not that easy, but everything was perfectly done. And then the new exciting operation was the impact experiment. I will show you later. And then we are up here. The departure, we departed the asteroid Ryugu in November of last year. And then by the end of this year, December the 6th, now I think it has been announced officially, so that I can say it, that we will have the Earth return of capsule. Hopefully it will work really well. And then sample analysis will happen, and the international sample AO is planned, but that's 18 months after the Earth arrival. If something happens to the return, it will be postponed, but I don't expect to have this postponing. I'm not going to talk about too much of a spacecraft and then instrument suite, but we have cameras, LIDAR, near-infrared spectrometer, mostly toward the 3 micron range. This is a major difference from Hayabusa, the original. And also thermal infrared camera is a new addition, supposed to XRF. And then 4 small landers were carried. In particular, this MASCOT was very important for us because it's got good cameras and then the magnetometers and the thermal detector and the spectrometer. And then those 4 were successfully deployed to the surface of an asteroid. Okay, so this is a timeline of observation. Not going to talk to you about too much of a detail, but as you can see, as a function of time since the arrival to the departure, the distance or the altitude from the surface of a Ryugu to the spacecraft quickly went down from several hundred kilometers away of approach phase to 20 kilometers, 5 to 6, 5 kilometers, and then less than 1 kilometers, and then this one was 600. This is less than 100, and then following year we have a touchdown that's as much as 1 meter. So the amount of information we gathered was very, very quickly changing. Then came back to the preparation for the second touchdown, and also artificial impact crater. So another busy session. And then the second touchdown was conducted on the 11th of July of 2019. And then we left the asteroid. Okay, So this is just some examples of the images we gathered. This is from 20 kilometers away from the asteroid. This is from about 5 kilometers away from the asteroid center. You can see a lot of boulders covering the surface. By the way, those data has been publicly available for research from JAXA ISSI DARTS site. If you just hit ISSI, Hayabusa 2, and DARTS, you will probably, Google will probably tell you the right URL. You don't have to copy this whole thing. But yeah, so this is something we analyze first. A lot of details, but when we went down really close to the surface, even more details was found. This is my favorite pictures of close-up images. It's got a lot of information, a lot of boulders, but again, here's the rather flat boulders with the imbrication along the slope of Ryugu. This lower part is close to the equatorial ridge where the geopotential is higher. This is toward the mid-latitude where the geopotential is lower. And then the material was sliding from the bottom of this image toward the top of this image. The implication is consistent with this direction of the mass motion. Also, there is a regolith run up to this imbricated boulders. This is also another piece of evidence support the material mass flow is from the bottom to the top of this image. Also, there's a bridge, but I don't think I have the time to discuss about this. But mass motion, finding of a mass motion was very exciting because we see a similar imbricated boulders with a regolith run up, many locations along this equatorial ridge, from the top of a ridge toward the mid-latitude, top of the ridge to the mid-latitude. So material is eroding away this ridge of Ryugu equatorial region. And then that seems to be consistent with this blue-red color banding, banded pattern of a color rather. The blue region is seen in this ridge, and it's probably due to the exposure of fresher material by this erosional process. So material is flowing again from equator to the mid-latitude. This color is consistent. And then furthermore, the shape modeling indicates that in the past, if the Ryugu was spinning much faster, like 3.5 hours per period, as opposed to current 7.63 hours per period, this shape has agrees with about 30 degrees of angle of repose. We don't know exactly the angle of repose, but that does not contradict with the other circumstantial evidence, and then also all the way from the top of the equatorial pole to the polar region to the equator is concentrated around the 30 degrees of a slope, and then that would be really consistent with the deformation of a Ryugu and then the generation of the current topographic shape at the time of a faster rotation. And then this is still inference, but I think it's a good inference. And then that is consistent with the sliding of material from equatorial region to the mid-latitude, because if the past spin was faster back then than now. So those material motion is getting really understood by our observation. So that was good finding. So we have a little control, we have a little understanding of what kind of a mass motion and then age relationship on the surface. Yeah, another piece of evidence very important for understanding the surface evolution is the SCI impact experiments. Crazy impactor was launched from this angle to this surface. As you can see, small crater began to grow very rapidly. Over here, the scale bar is 25 meters here. Large crater was formed. I think it was the first time to see the crater growth from the beginning to the end by the spacecraft. And then here's a motion, the frames. As you can see, there's no detachment of the ejector curtain from the asteroid surface. If the material, surface material has got some appreciable strength, the ejector curtain would be detached and then retained in the surface, and then the rest of the ejector curtain should have been just going. But the fact that the ejector curtain was continuous all the way to the surface of Ryugu is that it is probably controlled not by the strength, but the gravity, very small gravity of Ryugu. The surface must be very mobile. The internal cohesions or frictional cohesion between material on the surface of Ryugu was very loose, very small. It could be really easily detached from each other. So the crater size was probably determined by the gravity only. And also resulting crater size is exactly consistent with the gravity controlled scaling we found in the laboratory scaling. So that really allows us the very accurate crater retention age estimate. And Morota et al., it's not revision, it's already published in the 2020 this year in the Science magazine. But he found both redder craters and then the blue craters. Blue craters are relatively smaller, but he follows a very good crater production curve. And then it just has a smaller number density. And then we figured that those are probably made after the reddening of the surface ended. The red crater was formed before some reddening event happened. And there's a dichotomic by double peaked distribution. Blue crater tends to be clustered together in a blue region. There is no much population in intermediate color. Redder one's very red. So the redding event is not very diffuse. It must have terminated very abruptly. And then also the thickness of red material is estimated to be about 1 meter or a little less. That's actually consistent with the thermal skin depth of a Ryugu material. And that makes us suggest, makes us infer that this redder material may be a solar heated material on the top regolith. Ryugu may have experienced the orbital excursion. A lot of dynamical orbital calculation has shown, I forgot to mention Patrick's paper here, but those theoretical calculations show that it's quite possible that those near Earth asteroid could have been had an excursion really close to the Earth, close to the sun, but the excursion could be terminated very abruptly by another encounter to the large object like Venus or Earth. So termination of a reddening or a color changing event is very likely. And then age of those blue crater retention was only 8 million years. And then if you assume the near Earth population, the red curve craters is actually also the same age if we assume this main belt population. We could use a near Earth population, but that would be much, much longer, like 200 million, 500 million, some very large number. And then that's actually longer than the lifetime, collision lifetime of Ryugu, so it's not very likely. So this red crater and then the blue crater age, probably age from the beginning of formation of its current shape. And then this age is probably the age of age of this current orbit after experience a reddening event. So I think we found the evidence to show when the current shape was formed and when the current orbit was attained by this asteroid. And then, so this is also one major stage of evolution deciphered, but we don't know where this C-type asteroid is coming from yet. So this is the recent evolution. Okay. I think I have to really hurry up. And then changing gear a little bit. Now I am trying to talk about the parent body, or this part of the story. The top shape we talked about, and the spectra of Ryugu was actually very surprising. The telescopic data we obtained before arrival had a lot of different varieties, but only some of the spectra were consistent with what we observed. I don't think you can really see this very well, but there is a stack of 12 different spectra taken at the 12 different rotational phases. But those are identical, really identical. By this I mean there's not much of a spatial variation of the spectra of Ryugu. And this spectra is very flat compared to typical carbonaceous chondrite spectra. And then the best match I thought we found is a thermally metamorphosed CMCI. Some people say ATCC, aqueously altered and subsequently thermally metamorphosed carbonaceous chondrite. Those are too wordy, so ATCC. But the thermally metamorphosed carbonaceous chondrite. And then those spectra are consistent with the Eularia families and the Polana families. Ryugu is, I think, a 90% of chance coming from this inner belt, like Itokawa, because the origin is very likely from New 6 from a point of view of a dynamical calculation. But there are not that many large C-type or this CB type families in this main belt, and also large enough to be able to deliver Ryugu size fragments to the New 6. So identification of a family for Ryugu and also Bennu is a much more straightforward than that for Itokawa. So I think I think we're much confident about the origin of Ryugu from Polana and the Eularia. This really helps us infer the parent body evolution. But more surprising thing was coming from the near infrared spectrometer. This near infrared has a very weak absorption band at the 2.7 micrometer range. This is the band for OH band. And then in a classic carbonaceous chondrites, so-called hockey stick type of absorption with a triangle shape, like Ivna or Murchison or called Bocabel, the same type chondrite. But and actually Bennu, it's got very similar shape, very classic OH band. But the Ryugu doesn't have such a hockey stick shape band. It's also very weak. And then the best match we could find is this Ivna, heated Ivna. Also, heated Murchison is also quite similar. But those carbonaceous chondrite that does not have a very substantial amount of thermal metamorphism do not seem to be consistent with these shapes. It's not really a final answer, but I think it's a very strong case. So this really makes us think that the Ryugu material may have experienced the thermal metamorphism. There are other types of scenarios, but this is one possibility. And then after seeing this news 3, we began to analyze each individual boulder spectra. It's a very busy diagram, and then I don't have that much time to explain the details, but morphologically, there are at least 4 types of boulders, and then those boulders on the regolith are concentrated around this region in this, again, principal component analysis results, the principal component space. This principal component space was defined by the main belt asteroid distribution. Those are red spots and then light blue spots and then the yellow spots are C-type asteroid in the main belt. This one was using Binzel and Basan Binzel 2002. This entire plots was the distribution of a C-type main belt. Compared to this large range of C-type asteroid distribution, Ryugu distribution is very confined. And also, this is consistent with the location. This is along the dehydration track of Ivna or Murchison. Those are similar to the near-infrared spectra. It's still circumstantial evidence, but it is consistent with the dehydration. Well, not completely dehydrated, but the moderately dehydrated spectra of those meteorites seem to be consistent with Ryugu. And then the fact that those are concentrated around a very narrow range of temperature range, if we believe this is a dehydration track, we thought that Ryugu parent body may have been quite uniform in its interior rather than very wildly heterogeneous interior. More recently, oh, I forgot to mention this the citation, but this is a recent JPGU presentation by one of my students, Koki Yumoto. He did a very thorough analysis of boulder color statistics. The reflectance factor, well, similar to albedo, is very confined, very highly concentrated around the narrow region of value. This is the different types of typical carbonaceous chondrite. Original spectra was here, and then after heating up to 1,000 degrees, it changes quite a bit. Murchison, and then also Yamato, 793595, and then Dofer and other experiments exhibit a large range and, of temperature, spectra. Compared to those variations, Ryugu is very highly concentrated. Actually, Bennu also has a very highly concentrated color, although the very small amount of boulders have a very wide range of spectra. The vast majority is very narrowly focused. So those picture seem to be consistent with this type of a large uniform interior of a bold parent body as opposed to equally spaced temperature structure. It's still circumstantial evidence, but this is my preferred structure. Doesn't mean that this is the really right answer. As I show you in a couple minutes, there may be another thing. So putting all those things together, now we have a working hypothesis that you use parent body to radiogenic heating, a very homogeneous heating, and then disruption, and then high spin rate, and then erosion, and the orbital excursion, and then a banded structure like current shape with the possible age time markers on a different stage of evolution. This is a sort of a breadboard model that should be revised or denied by the upcoming geochemical measurements. So that's my conclusion. But my conclusion is not the conclusion of the entire, oh, this is a bad copy, but the very important piece of evidence. The entire science has to be more careful. For example, MASCOT lander found a very interesting result. The MASCAM measurement showed that a lot of inclusion on the surface. It's a very small, several millimeters, but many of them. It shows two different things. One is the inclusion itself. There are not that many the carbonaceous conduct that has that large inclusions. One example is the Turkish lake, but some others, but most are not as dark as Ryugu, so it's hard to figure out. But the Turkish lake might be a possibility, as indicated by suggested by Yauben. And then another thing is that it shows that there's no thick regolith or the fine grain dust cover on the surface. Otherwise, it would be very more mud and then smooth. But such a fine structure should not be visible. And that is consistent with the MARA measurement with the thermal infrared. I'm sorry about this, a bad copy, but the nighttime measurement had a very good thermal inertia measurement. Without the dust layer, the measurement is very consistent with the model. But if you assume a little bit of a dust layer, very thin, less than 0.1 millimeter dust layer, then you would violate the observation. So the dust isn't there. And then, so that's one thing. And then the inclusion and the texture has to be explained with the comparison. So at least we have 3 different models. And then the last model of moderate dehydration is this calculation of a catastrophic disruption. This is a work by Patrick Michel, recently published in Nature Communication. Large project, the target must have been disrupted by another impactor, as I talked about. I don't think there's not much question about it. But what was questioned is the degree of dehydration. Until recently, until this work was done, not much dehydration was possible. But as he showed, a lot of red spots that has experienced several hundreds of degrees of temperature. That's large enough to be able to expel some of the water from a view. So that has to be examined when the sample is back, right? Getting really over the board. But there's a good news about this. Out of the 3 hypotheses, there may be more, but the best news is that we got the samples. This is the motion pictures taken at the time of the first touchdown. Just go back again. This is the oblique view from so-called CAM-H, looking at the sampling site. This is a nadir-looking wide-angle camera. Surprising thing is that at the time of a touchdown, Oops. Bad at the, okay, I'll stop somewhere here. At the time of touchdown, the whole entire scene get darkened really quickly, and this is coming from the dust um, um, coming from this point of the touchdown, and this is another same view. Uh, the streak of a dust is coming from the side of a touchdown, and also this dark rock changed its color to a brighter color from before the touchdown to the after touchdown. So I think there must be some kind of a dust on the surface, although it's hard to figure out why thermal measurement doesn't have the thermal influence of such a thing. So it's hard to really make sense out of this, but this is something we will probably find out. Also, another thing is that the camera has lots of a dust particle on the lens. Those circles are really the sign of contamination on the surface, and I was very worried about the outcome of this lens contamination. But so far our spacecraft is doing fine. So fine dust must have been hiding somewhere that we couldn't really see from the camera or the image. Another piece of evidence that I want to show you is that the ejector curtain or ejector blanket from an artificial crater was clearly shown in this highly stretched image of ONCT. And then the side of a touchdown 2 is around here. There's some ejector blanket continuously. It's not that thick, but it's still there. And then, so the second touchdown must have obtained some bit of a ejector blanket. And then the depth of the crater is almost 2 meters. So this is deeper than the thermal skin depth, which is probably 50 centimeters up to 1 meter. So this touchdown 2 must have some bit of a very fresh material. Free from space weathering for sure, and then hopefully free from solar heating that we think we found. So sorry to getting over the time. This is the summary of what we think we found from Hayabusa 2. But the most important message is that we will have the sample to the Earth in about half a year. And our team members are working very hard. Today we had the team meeting for the last observation at the time of Earth return. And then, so things are doing well. So hopefully we will have a good report to you in December. And then this is the end of my talk, and thank you for your attention.
Yeah, thank you very much, Seiji. I mean, this was very interesting, and it's actually, you know, showing how this mission really changed our understanding of asteroids. And actually, I have a model of Itokawa here.
Oh yeah,
that gave me, you know, some years ago. Unfortunately, we ran over time, but you know, our we don't have a hard deadline, so if you hang around for a few minutes more, we could allow a few questions if you know, people were interested to ask questions. So please, I mean, raise your hand with the software if you have a question, and then Zolila will turn the microphone to you, and we'll have something like, you know, 3 questions or so, or maybe 5, you know, whatever. So is there a question out there?
Yeah, there's a question from Roger Maurice Bonnet. I will just activate him. So yeah, please go ahead, Monsieur Bonnet. You have to unmute your microphone, please.
Can I do that? Well,
Okay, we go to the next one, Thomas Müller. I will, yeah, can you unmute your microphone and ask your question, please?
Hello, I just unmuted. Can you hear
Okay,
me?
yeah, that's good.
Yeah.
Now we hear you.
Very nice talk. I liked it very much. Very nice summary of both missions.
Thank you so much.
I have one question about the resurfacing processes and the time scales. I think I missed some of the points. Could you repeat a bit history of the surface and the history of the whole body, like when it came from the inner main belt, when it collided, and what are the time scales again? Yeah, I think it was this slide.
Yeah, I was really rushing through. The first, let's say, maybe I should come from the big, more recent time. The ending of orbital excursion to the sun was probably around 8 million years. This is based on the fresh color crater statistics. And then this is already near Earth orbit. Some people suspect that near Earth orbit is, it's kind of, I guess maybe I'm not going to talk about this too much detail. Okay. And then this time is the residence time in the main belt. It's about 8 to 9 million years based on the, again, crater statistics, but based on the main belt impactor population using the same type of crater scaling. This is the age when the current Ryugu shape, including the top shape and then the equatorial ridge, was formed. And then the breakup time was either 1.4 800 million years ago, depending on which families are the hometown of Ryugu. This is not from the direct evidence of Ryugu, but the indirect inference based on the matching of those spectra and then their disruption age based on the Yarkovsky migration of a family. And then original time is 4.56 billion, but this is pretty much age of a solar system. Just assume that their age is as old as other carbonaceous chondrites we see on the surface of Earth. But the last digit could be unknown. It could be very different depending on which type of asteroid. So I'm just sort of taking the age here. So just a generic age. So those are the 3-4 different ages. Did I answer your question?
Yes, thank you. This is very interesting. I'm very curious to see if things are confirmed then by the samples coming back. So
yeah, I'm very curious about the last digit. Thank you.
Okay, thank you.
Okay. The next question is Monsieur Bonnet, please.
Yes. Do you hear me?
Yeah, we hear you.
Yes.
I would like to thank you very much for a fascinating and very interesting mission. You are offering us a genuine game changer set of missions. This is unique. My question is, to what extent do you think asteroid mining, considered in the future by some people, is a realistic concept? In other words, to what extent your two missions offer arguments to support future efforts in this field?
Yeah, it's a very interesting question. I am very curious and interested in asteroid mining. I don't know how feasible it is in terms of the economy or the technology. I'm not really an expert of that. But the one thing I can say out of my own experience with Hayabusa and Hayabusa 2 is that there are a lot of unknowns we learned out of this surface contact. It looked like there's very dust-free environment before we touched the surface, but all of a sudden a lot of dust came out and then our lens got really contaminated. Those factors should be included. And then also the surface is very mobile, so probably grabbing some pebbles and rocks are probably not as hard as we were afraid of before. So those are two different pieces of, I don't know if that answers your question, but that's what I can say for now.
You did the best to answer. Thank you very much.
Thank you.
We have a live question. If you click on the Q&A, there's a question from Anastasia in Zoom. Or I can read it for you. She says, you see it?
Oh, okay, yeah.
Okay, yeah.
This is from university. Are you able to put the lower limit on the amount of water content based on the OH line that you showed, and then is shallow layering structure help to contain water even more? It's a very good question. Unfortunately, I don't think we can put the lower limit of the amount of water right now. We can infer those water amount by assuming that the surface of the Ryugu surface is similar to even 500 degrees and things, but it's a little bit too much thing to assume. It's not. I wouldn't say it's an observational constraint. It's an inference. I think it's like more than half of the water would have been lost by the time it was heated up to 500 degrees, but it's more like a speculation. That's as much as we can push, and then I wouldn't be too surprised, unfortunately, if my answer is completely wrong at the time we get the sample back. And then talking about the layering structure. This is a work in progress. It's a very good question. The people are still analyzing the data by comparing the before and after the SCI cratering. SCI cratering punctured through the possible solar heating layer. So we could see the solar heating free range. But I'll just say that the spectra didn't look too different. That's as much as I can say without really correcting it like next week. I don't know the outcome yet, but the solar heating may not have play that important role in changing the water. That's my understanding, but it's a work in progress, so stay tuned, please.
Okay, there's another question from Manuel. Could you please unmute your microphone and go ahead?
Thank you very much. Thank you for the interesting talk. I was very curious about the strength estimates that you mentioned for the first impact that you estimated based on the dust curtain. And I wanted to ask if there are also strength estimates for the second touchdown.
Second touchdown, I don't think we have that much of a strength estimate. Yeah. The phenomena we saw in the first touchdown, second touchdown, we didn't see that much of a difference in terms of the dispersion of the material. So I can say that it's very mobile.
So thank you very much. It's really exciting to see the estimates from the first touchdown.
Thank you.
Okay, are there more questions, Saliba, or?
Yeah, there's just one coming up.
Just take this question and then we.
Yeah, there's somebody's raising the hand and somebody has a question. So let's go to K. Kruger, bitte. Please unmute your microphone, please.
Yeah, hello.
Yeah, we can hear you.
Hi.
In Germany. So thank you for your very nice talk. This was very interesting, very nice overview talk. My question is, you mentioned that Bennu and Ryugu may originate from the same parent body. I did not understand, is this this conclusion mostly derived from the similarity in their composition and spectral properties, or is this also consistent with dynamical calculations of their trajectories back to the past?
Okay. My answer is yes to those two questions. It's more like the situation is that there's no much good way to say that those two bodies are from two clearly different parent bodies yet. Although we don't have that strong evidence to say that those are likely to be from the same parent body. The situation is that we have two large parent bodies in the inner main belt. Both of them can deliver Bennu size or Ryugu size fragments to new 6. And dynamical calculation says that Polana is a more likely sources for two bodies just because the Polana is more widely dispersed than Eulalia. And then spectrally, visible spectra wise, two bodies are actually very similar, Ryugu and Bennu, and Polana, Eulalia. We don't have good data for the 2.7 or 3 micron absorption for those families. Ryugu and Bennu are very contrastingly different, but those family data are not available. So once we actually see the 3 micron range of a spectra by the telescope, the astronomer can answer our questions. So that's the situation. But when we get the sample back, we will be able to tell the difference or the different types of parent body or same parent. So that's the situation.
There's a question in the Q&A. There's a question, please.
That's a comment, actually.
Comment.
Okay. So maybe let the comment stand and Seiji.
It's just a comment.
Okay, I'll read it. Yeah. Thank you.
Okay, thank you very much, Seiji. This has been a very exciting talk, and it was a very good starter for our new seminar series. Thank you very much for attending, participants. I think at the peak we had something like 160, which is a very good number for the start. We'll reconvene in 2 weeks' time for a talk by Alan Stern on the New Horizons missions on August 13th. And just be aware that that talk will be at 5 p.m. Central European summer time. So we're shifting a bit to accommodate the time shift to the US, where Alan is reporting from. So with that, I'd like to conclude this first Game Changers seminar. And again, thank you very much, Seiji. Thank you very much to people joining us, and see you next time. Bye-bye.
Thank you, Thelma. Thank you, everyone. Goodbye.